Welcome back to the video lecture series for Introduction to the Art of Programming using Scala. This is the third and final video where we will look at mazes. In the last video we did some animation to help you understand the maze algorithm as it was written, and we talked about the fact that maze algorithm literally checked every single possible path in order to find the shortest one, and that can be kind of slow. So in this video we're going to look at how we might be able to speed that up a little bit, what changes we could make to the code to make it run faster. So what I'm going to do is I'm going to copy this function of shortest path, and we're going to make an altered version that is potentially more efficient. So if we copy and paste this, I'm going to make a shortest path, we'll call it shortest path 2. Now, how are we going to go about doing this? Well, our current shortest path puts down breadcrumbs and picks them back up when it's done working. Some of my students, instead of thinking of these as breadcrumbs, think of it as kite string. Okay, where as you walk down, you reel out your kite string, but then when you walk back, you roll it back up. For this, we're going to stop rolling it back up. But we have to be smart about how we're going to do that. We're going to use what I refer to as smart breadcrumbs. Okay? In this case, our breadcrumbs are going to keep track of not just whether or not we've been in the room, because right now all that our breadcrumbs do is either say, yes, we've been here, no, we haven't. We're going to leave an alternate type of breadcrumb, which says, I've been in this room before, and this is how many steps it took me to get here. And so we're going to pass in another argument to this. That is how many steps we've taken to get to the room at XY. Okay. And the first part of our code stays the same. If you get to the end, it's 0. If you go out of bounds, you run into a wall, it's a big number. But we're going to add another case here. This other case is the situation where you're not out of bounds, you didn't run into a wall, but we ran onto a breadcrumb. And this breadcrumb says that we've gotten to this room previously, but we did it in fewer steps than what we are at right now. So if maze sub x sub y is greater than 0, because if it's 0 then we haven't been there before, and maze sub x sub y is less than or equal to. Okay, if we've been to the room with the same number of steps, well, then that's good. We don't need to keep going. If those two cases are true, so if we haven't been there before, but when we were there last time, we got there in fewer steps, that means there is no point in me continuing to go. If there was a shortest path off of this location, I found it the previous time when I got there in fewer steps. Any work that I continue doing now when I got there in more steps is going to be inefficient. And so this is just going to break out of the recursion basically by returning our big number and then come down into here. Now, this changes some things up though. We need to return we need to leave breadcrumbs not just saying they're all -2, but instead it needs to leave steps. Okay, so the way I have to think of this, instead of just being a simple breadcrumb that doesn't show any information except whether or not you've been there, this is like a little piece of toast that's had stamped on it or burned into it a number, which was how many steps it took us to get there. The other thing is we're not going to pick these up. Okay, we're going to leave them behind because we need them to be there when we revisit the same rooms. And I need to change my recursive call to use this modified version. And when we do the recursion, we're calling it with steps plus 1 because we've now taken one additional step. Okay? So the algorithm fundamentally looks very similar, but we're not picking up our breadcrumbs. We're making it so that our breadcrumbs aren't just Boolean values, they actually have a numeric value to them. And we're making it so that if we ever come across someplace that we've been before, and if we got there before in fewer steps, we're just going to break out. In order to make this so that it works nicely with our animation, we need to add one more situation here, which is the so if it was 0, we colored it white. If it was -1, which is a wall, we color it black. And then otherwise we were coloring it red because that's what our breadcrumb was. Well, now our breadcrumb might not be just red. So this works with the code we had before and the code we're doing now. If maze sub I sub j is greater than 0, then what I want to return is, actually, I'm going to make my own color. I'm going to make a new color that is red, but it's going to be red, let's say 30 steps is about the longest for this current maze. So how about 20 plus 5 times the maze sub I sub j, and just to make sure we'll take the minimum of that and 256 because we can't, 255, because we can't go over 255 when we blend our colors. They're only allowed to be between 0 and 255. And let's see how that works. See if we typed everything in correctly. Nope, I need an else here. And it looks like on, well, let's see. Is that carryover? Apparently so. Okay, now this is still using the old algorithm, which of course spends lots of time. So you can see, yes, this spends lots of time running around. What if I change the call at the end here to use shortest path 2? And we're going to start off saying, hey, this is our first step. Now I run this, and we're done. Oh, almost. We'll spend a little bit of time. Boom, 30. Okay, so you can see that it did a little bit of extra work in there. This winds up being color-coded so that the darkest reds are short numbers of steps, but you can actually see that we wind up making a gradient in here. So from any location, we want to step on the next darkest square, and we wind up with a fairly bright red down here, and then it goes downhill as we walk back towards the exit, and that gives us our shortest path of 30 in there. Clearly, that didn't take as long as the one before, and so this is an improvement. It turns out this is still not optimal. So by the algorithm that we're doing here, when we use recursion, this is something called a depth-first search. It actually took each path and it walked it as far as it could go until that path ran out, either by finding the exit or hitting someplace where it couldn't go any further. And then it steps back, and then it tries another path as far as it can go, and then it steps back and it tries another path as far as it can go. When we're looking for the shortest path, it turns out that's not necessarily ideal, because if you're looking for the shortest path, you don't want to keep going and going and going and going until you hit a dead end. There might be other routes where you hit the end a lot faster. And so ideally for a shortest path, you're often what you want to use is something called a breadth-first search. Now we're not going to talk about breadth-first searches here. They're kind of a more advanced topic. But by putting down the smart breadcrumbs, we can still make it so that our depth-first search is at least smart enough to terminate out more intelligently and be more efficient about what it's doing. So that's it for this video, and we'll come back next time and we will look at some different sorts that we can use that use recursion and wind up being far more efficient, especially for large n values, than the ones that we did previously.